Now let's work an example of a correlation problem. The following paired data is a random collection of observations of the Old Faithful geyser in Yellowstone National Park. The duration of the geyser eruption, the X values, and the associated interval after that eruption, the Y values, are both given in minutes. Use a 0.05 significance level to test the claim that there is a correlation between eruption duration and the interval after. And specifically, we're looking for a linear correlation. So let's look at our data. So again, the X values are the duration of the eruption. The Y values are the interval after that specific duration. So after a 3.6 duration of eruption, there was a 79-minute wait until the next eruption. So first we'd like to see the scatter plot of this data. So let's enter this data in lists in our calculator. Okay, so stat, edit, and in list 1 we'll put the X values, 3.6, 1.8, 3.33, 2.28, 4.53, and 2.88. In list 2, we'll put the associated Y values. So the Y value that's paired with 3.6 is 79, with 1.8 is 54, and 74, 62, 85, and 55. Okay, to create our scatter plot, we want to use this stat plot function, so we say second, and then we click on this button, the Y equals button, to get the stat plot. If we now click on the enter button twice, that will turn it on. Notice how on is blinking. And then we want to select that first graph type, the scatter plot. Then we need to set our X list. It says L1, and that is where my data is, but I would change it if it was somewhere else. And my Y list is in L2. And finally, we want to pick the symbol that marks the points, and I'm going to select this first one here. Okay. Now we want to zoom, which is the middle button up here on the top row, and I want the 9th function, so I could just say 9, zoom 9, that's zoom stat. Okay, so now we have a visual representation of our ordered pairs, and it does tend to look like a positive linear correlation. They're not on a perfect line, but we do tend to see that as the X values, the durations increase, the Y values, the interval after, also increase. Okay, now let's follow through with our hypothesis test. So it's given that we're to use a significance level of 0.05. We have a sample size of 6. There's 6 sets of ordered pairs here. So we'll need to find our null hypothesis, and recall it's always going to be that the population correlation coefficient is 0. In other words, there is no linear correlation between these two variables. Our H1 will always be that rho is not equal to 0. We're always going to have these two symbols for HO and H1. So we'll find a critical value, and then a test statistic, and a p-value. And we'll make a decision. So let's look at our decision diagram. Okay, here's 0, no linear correlation between the two variables. Here's +1, a perfect positive correlation between the two variables, and we know it's not perfect because those dots weren't in a perfect line. And -1, a perfect negative correlation between those two variables. And after seeing the scatter plot, we don't expect to see anywhere near this because our slope was positive. It was going uphill. Okay, to find our critical values, we use the table in the back of the book. It may or may not look similar to the one we have here, but let's pull up the one I have. And so we have a two-tailed test, an alpha of 0.05 and an n of 6. So we have 0.811 as our critical R. These are critical values of R. But of course we'll have a positive and a negative of that same number because we have a two-tailed test. Okay, so let's get those on the graph. Here's -0.811, positive 0.811. And now that gives us a critical region. Here's our shaded region. Okay, now we're ready to run our test. Okay, so we'll go to our stat tests and find our linear regression t-test. There it was, linear regression t-test. Okay, x values, it's already on L1. If it wasn't, I would change it, but that's where my x values are. My y values are in list 2. Frequency is always 1. Just leave it as 1. And our type of test is always two-tailed, so this should always be highlighted. We won't need to enter anything in this field, so we'll just go down to calculate. Okay, so what we need from this is an R test statistic and a p-value. First we see the p-value here. We're going to round to 4 decimal places. It's 0.0140, but the next digit is a 5, so that's going to round up our fourth digit to 1, 0.0141. Now we'll have to tab down to find R. There's R squared. We need R. 0.9015. We're going to round this to 3, so it would be 0.902. So our test statistic is R is equal to 0.902. Remember, our critical value is also an R. I just didn't write it there, but these are all R's. And our p-value 0.0141. Okay, so now I need to find where my test statistic would be on here, and it would be somewhere in this area. Okay, so does the test statistic fall in the critical region? Yes. Is my p-value less than alpha? Yes, those should agree, and when that's the case, we reject the null hypothesis. Now our claim is always going to be that there is a linear relationship between the two variables. Our null hypothesis is always going to be that there is not a linear relationship between the two variables. So remember, when that's the case, rejecting the null hypothesis says that we have evidence to support the claim because they do not correspond to each other. Rejecting HO means that our conclusion is there is sufficient evidence to support the claim. of a linear correlation between eruption duration and the interval after. So this evidence we're speaking of, what that is our sample data. Sometimes you see there is sufficient sample evidence because that is what our evidence is. We have this claim and the evidence we're using to test our claim is here, our paired sample data.